Welcome to the Substation Primary Design course, specifically Part 2 focusing on 125 VDC battery and charger sizing, created by engineer Sharif Hussain. This educational video for engineering students and professionals will guide you through a practical example based strictly on real substation design principles from IEEE standards. In this part of the series, we will delve into a detailed practical example for battery sizing, using a substation single-line diagram that includes bus bars, circuit breakers, disconnect switches, transformers, current transformers, potential transformers, and protection relays as the foundational basis for our calculations. Our engineering proposal carefully considers specific load conditions that occur during the critical tripping time, encompassing both momentary loads like those from tripping operations and continuous loads that persist throughout the event, ensuring reliable power for essential systems. This scenario involves a high-voltage line feeder trip, accompanied by a transformer feeder trip and the tripping of all medium-voltage switchgear, in addition to the momentary loads from control and protection panels, simulating a realistic fault condition in the substation. At the restoration time, once the fault is cleared and isolated, we account for the closing of one high-voltage breaker along with the simultaneous closing of an incomer and an outgoing feeder from the medium-voltage switchgear, representing the steps to bring the system back online safely. We also precisely account for a spring charging motor starting up, including its significant inrush current during startup, as well as one motor that is already running continuously, both drawing power from the 125 VDC battery during this phase. Additionally, emergency loads such as critical lights fed directly from the battery are assumed to operate for a full 3 hours, providing illumination in control rooms and corridors during the extended outage period. The continuous loads, primarily consisting of control and protection relays essential for system monitoring and automation, are fed from the battery right from the beginning and continue until the very end of the specified battery discharge time, ensuring uninterrupted operation. After meticulously summarizing all these identified loads based on our specific substation configuration and engineering proposal, we proceed to compile a comprehensive load summary table for further analysis and duty cycle calculations. L1 represents the continuous load at 80 amperes, which must be sustained by the battery for a full 12 hours throughout the entire duty cycle, covering relays and other persistent DC requirements. L2 is the momentary load peaking at 450 amperes, lasting for just 1 minute right at the beginning of the event, capturing the high inrush from initial tripping sequences. L3, the emergency load, is rated at 10 amperes and is required to last for 3 hours, typically powering essential lighting and minimal systems during the outage. L4, the restoration load, stands at 40 amperes and applies for 1 minute at the very end, accounting for the closing operations and motor startups during system recovery. With these load values now clearly defined, we apply them directly to our duty cycle calculations as per IEEE 1115 standards, breaking down the battery performance into distinct time periods for accurate sizing. Period 1, from the start, combines the continuous L1 at 80 amperes with the high momentary L2 at 450 amperes, resulting in a total demand of 530 amperes for the initial 1-minute duration. Period 2 follows immediately, consisting solely of the continuous L1 load at 80 amperes, extending until the emergency phase begins, representing the steady-state draw after the initial surge. Period 3 then combines L1 at 80 amperes with L3 emergency at 10 amperes, totaling 90 amperes over the 3-hour span from 180 to 360 minutes, ensuring backup for critical functions. Period 4 returns to only the continuous L1 at 80 amperes, maintaining this level until the final restoration phase, underscoring the baseline requirement for the battery. Finally, Period 5 combines L1 at 80 amperes with L4 restoration at 40 amperes, yielding 120 amperes for the last 1-minute interval at around 720 minutes, completing the duty cycle. This video details the calculation of battery ampere-hour capacity and charger sizing, adhering to IEEE 1115 standards. We begin by studying the duty cycle to determine the battery ampere-hour requirements. Section 1 considers only period 1, where the load is 530 amperes for 1 minute. We apply the battery manufacturer's KT factor of 1.09 and a temperature factor TT of 1.1, resulting in 635.47 ampere-hours for this section. Section 2 includes period 1 and period 2, with a load of 530 amperes for 1 minute, lasting 180 minutes. Applying a KT factor of 3.83 and TT of 1.05 yields 2,131.4 ampere-hours for the first part of this section. For the second part, with a load change to 80 amperes for 179 minutes, and factors KT of 3.81 and TT of 1.05, we get minus 1,800.22 ampere-hours. The total ampere-hour for section 2 is 2,131.4 minus 1,800.22, equaling 331.175 ampere-hours. Section 3 incorporates period 1, period 2, and period 3, following a similar calculation methodology. For section 5, the total uncorrected ampere-hour value is 1085 ampere-hours. To obtain the actual battery capacity, we apply correction factors, an aging factor of 1.25 and a design margin of 1.1. Multiplying 1085 by 1.25 and 1.1 gives an actual battery ampere-hour capacity of 1492 ampere-hours. From the manufacturer's catalog, a 1600 ampere-hour battery is selected. Next, we move to charger sizing. Here, I is the calculated battery charger output in DC amperes. A represents the battery ampere-hours, which is 1,600 Ah. T is the recharge time, set at 16 hours as per standard. E is the recharge factor, 1.1 for lead-acid batteries and 1.3 for nickel-cadmium batteries. IC is the continuous DC load current, which is 80 amperes. D is the design margin factor, 1.1 if not specified in the project technical specification. Finally, K is the altitude correction factor, considered as 1 if not specified. Applying these values to the formula, the required charger current is calculated to be 231 amperes. This systematic approach ensures accurate battery and charger sizing for reliable system performance. Thanks for watching this detailed video on substation primary design for 125 VDC battery and charger sizing. Please share the video with your colleagues and subscribe to my channel for more engineering content from engineer Sharif Hussain.